Welcome to Inside the Apple T2. This is the Jasmine Room. The speakers today are Mikhail, Davidov, and Jeremy Erickson. A couple of notes for you before we begin. The first one is to stop by the business hall located in Mandalay Bay, Oceanside, and Shoreline ballrooms on level 2. Also, the Black Hat Arsenal is in the business hall on level 2. I'd like to thank you for putting your phone on vibrate. It makes it easier for the rest of us to ignore it. So, with that, I'd like you to welcome our speakers to the stage. Thank you.
Thank you.
Of course.
Thank you. Stick this up here. All right. Well, hello everybody. I'm Mikhail Davidov, and this is Jeremy Erickson. We're both researchers on Duo's advanced research team, Duo Labs. Duo Labs is a team of hackers, researchers, and engineers dedicated to protecting the public by identifying and fixing security vulnerabilities on a broad scale. We do this by prototyping new products and conducting research into security systems used by the broader security community. I've been working in the information security space for over a decade as a security researcher and consultant. I primarily focus on vulnerability discovery, exploit development, and reverse engineering.
Hi, I'm Jeremy Erickson. I've also been working in the information security space for about a decade. I tend to work more on early prototyping of networks and systems, but I occasionally like to go and see how things work on the inside.
We're here today to talk about the T2 chip. The T2 is the successor to the T1. The T1 chip was the chip that powered the Touch Bar and Touch ID on previous generations of MacBooks, and the T2 is the next evolution of that platform. One of the new key aspects of the T2 is the greatly increased role that it plays in platform integrity and system security. Here today, we're going to discuss what the objectives of the T2 are, the T2 system architecture, how to get started analyzing T2 firmware and the embedded UEFI images, how the secure boot flow has changed in T2 systems, what accessible communication channels exist between the T2 and macOS, how to directly communicate and interface with exposed T2 services, and share with you some tooling to make this process a little bit easier. So, based on our research, we developed an understanding of what some of the T2's design objectives were. One of the main ones was to enhance privacy controls by providing hardware disconnects to certain peripherals like the built-in microphone and camera. This allows Apple to prevent malware from being able to leverage those peripherals in scenarios such as when the laptop lid is closed or the screen is locked. Additionally, they were aiming to better protect data at rest in a much greater capacity than has previously been done on macOS platforms. By mixing in key material only available to the T2, Apple was preventing offline attacks in scenarios where the physical SSD flash chips are removed. As the process of mixing in a password-derived key with the T2 secret happens directly on the T2, it allows Apple to throttle brute force decryption attempts. Finally, one of the most important design objectives of the T2 was to bring the same level of security and integrity protection available on iOS devices to the macOS ecosystem. So why are we, an authentication company, looking at the T2 in the first place? Well, at Duo Labs, we believe in the concept of democratizing security. We strive to enable other researchers to leverage our work to further the field. Understanding the security underpinnings of a system is critical to being able to trust it. And the more eyes there are on any critical piece of technology, the more latent vulnerabilities will be uncovered and can be fixed. The T2 is one of those leap-ahead technologies that enables new endpoint-centric enterprise security models and more insignificant investigation. Now that we understand some of the objectives of the T2 and why we're looking at it, let's look at what the T2 actually is. So in the Intel world, the T2 is referred to as an embedded controller. Most of you are likely familiar with the concept of a baseboard management controller, or BMC. BMCs allow for remote administration of a system. They're very commonly found in server architectures and are utilized heavily by the bare metal cloud industry to reset systems to a pristine state before provisioning new customers to them. The T2 is essentially a BMC minus the remote management stack. Embedded controllers are responsible for orchestrating various tasks on the platform, such as the very initial power sequencing, thermal management, power state transitioning, and interfacing with various onboard peripherals. The T2 is comprised of several components. Primarily, it's an ARM64 core based off of Apple's A10 design. Internally, it has a flash controller that deals with AES acceleration and storage of data on the raw SSD flash chips that are present on T2 supported platforms. One interesting note about this is that the SSDs that are present lack their own controllers and are just raw flash chips deferring functionality such as wear leveling and block allocation to the T2. You can't just unplug these drives, stick them in another computer, and expect to actually be able to read them out. There is also some internal storage areas for storing things like the T2 file system, the UEFI firmware, and other variables. Finally, there's what Apple calls a secure enclave processor, or SEP, which handles things such as encryption keys and Touch ID authentication. The T2 is connected to the rest of the platform via several common interfaces such as PCIe, MIPI, PDM, and eSPI, which we will get into later. But this architecture can be simplified to basically this, highly privileged, DMA-capable Apple Watch soldered to the motherboard that orchestrates and controls some of the most basic platform functionalities. Now that we understand a bit about what the T2 is, let's talk about what's actually running on top of it. The T2 kernel and operating system, collectively called BridgeOS, are closely related to the watchOS stack and inherit many properties from it. Say you want to actually look at this stuff yourself. As BridgeOS is a derivative of watchOS and by virtue iOS, a lot of the same iOS reverse engineering tools also apply here. You can go to the Apple software catalog and download bundled T2 firmware update packages or pull them directly out of a local system cache. You can extract these update packages with a combination of freely available tools, a walkthrough of the extraction process, and most of the tooling is provided by Jonathan Levin, and it's linked over here. If you extract and decompress the update packages, you will, inside will be an update bundle zip file which contains the root file system, a collection of kernel caches, which are the base kernel and all the kernel extensions baked into a single large file, and a similar set of golden UEFI images. While they are bundled, the iBoot and SEP firmware images are encrypted like they are on other platforms, so they're not as easy to actually examine. The /boot/firmware directory inside the update bundle contains Image4 archives containing signed golden UEFI firmware images. You can use Image4 tool to extract the single section out of these, but do note that these images actually do end up getting hot patched by the T2 during the loading process, as we'll see later. As these T2 update bundles are meant for multiple product lines, they contain multiple firmware images differentiated by internal Apple product names. For instance, the iMac Pro is the J137, and our T2-enabled MacBook Pro is the J680. Googling around for model information, we got some clues as to what the J174 and the J140K are. That leaves us the remaining J780 and J132 as likely candidates for the Mac Pro and the MacBook Air. Model-specific kernel caches are relatively easily accessible after decoding them with the Joker tool. From there, you can throw them into IDA and start your traditional ARM64 Darwin kernel analysis. I also highly recommend using the IDA kernel cache extension, as it makes reconstructing IO kit types fairly trivial. The base T2 file system is split up into multiple parts in the update bundle, and they need to be individually decompressed and extracted with the OTA tool. After extraction, you will be greeted with a very familiar Mac file system. So the combination of those three firmware parts form the basis of our analysis. But before we show how the T2 attempts to improve on Secure Boot, we have to understand what was wrong with the prior state of the art. So here's everyone's favorite diagram when dealing with UEFI, right? This outlines the 7 boot phases that a UEFI platform goes through. The code that implements this is the very UEFI firmware that Apple aims to protect and was traditionally stored in a SPI flash chip. At the very left side, you have what's called the security phase. It's pointed at by the system reset vector. It's the very first bit of x86 code that gets executed by the CPU when transitioning from a low power state such as sleep and hibernate or the very initial power on. It starts off in 16-bit real mode, does some initialization, and then switches over to protected mode before handing off execution to the pre-initialization environment and onward to locate and boot the operating system. If you, as an attacker, are actually able to gain execution in this initial security phase, you can effectively take control of the entire system. Even if the security phase did perform all integrity checking it was supposed to, who was there to check the integrity of the security phase? Once you're able to run code in this phase of execution, you can patch everything going forward and infect the final operating system kernel and do whatever you would like. So how is this infection process typically done in practice? Traditionally, on the motherboard, you have your chipset attached to a SPI flash device which holds the UEFI firmware and other configuration variables. Attacks are performed either through purely software means, if the platform is misconfigured, or through hardware-based attacks. The popular Evil Hotel Maid scenario comes to mind, where a malicious actor gains physical access to your computer, opens it, uses a chip clip to attach to the flash device, and overwrites the UEFI firmware payload with an infected variant. Apple wanted to mitigate this, and for them, the solution was to get rid of that vulnerable flash chip altogether. The Enhanced Serial Peripheral Interface, or eSPI, is Intel's spiritual successor to the low pin count bus, and it's used to communicate with embedded controllers and BMCs. It was recently extended on Intel Xeon platforms with a new feature called Slave Attached Flash. This allows ECs and BMCs to manage all flash access operations. Again, the main reason why this is an important feature is if you think about a bare metal cloud environment, you need to wipe the machine before you hand it off to a new tenant. And this functionality allows the BMCs to quickly reset the UEFI firmware or perform remote upgrades. The T2 utilizes functionality to try to enhance secure boot. Typically, this slave attached flash functionality is only found on Xeon chipsets, but as Apple is a very special partner, they got that functionality enabled for their non-Xeon lines like the MacBook Pros. So the T2 utilizes functionality to enhance secure boot. We're going to go from the model on the left, where the chipset talks to a flash device over SPI, to the model on the right, where the chipset talks to the T2 over eSPI. The T2 then becomes the arbiter of all flash access operations, which sounds great, right?
Of course.
Yeah. So now that we understand a bit more about secure boot and how the T2 is wired to the rest of the platform, let's talk about the actual boot process. Everything gets kicked off way before the power button is pressed, in a process Apple refers to as early boot. Here I'm going to describe the process as I understood it in BridgeOS 2.0. Apple has since released some new revisions since then, but the broad strokes should still remain the same. The T2 utilizes the same integrity protection features that are found on the iPhone and the Apple Watch. On the chip itself, there is an area called masked ROM. The masked ROM is comprised of software instructions and data that has been physically hardwired on the die and is completely immutable. There's no way to change it at all. This is the basis for what is referred to as a hardware root of trust. The masked ROM's purpose itself is to locate the T2 bootloader, which is iBoot in our case, verify its signature against the Apple root CA, which is co-located inside of the masked ROM itself, and transfer execution to it. The bootloader locates the BridgeOS kernel, cryptographically verifies it, configures its execution environment, and transfers control to it. Finally, the kernel sets up the userland environment and launches the root process commonly referred to as PID0 or launchd. From this, the userland services and processes are started. Launchd has an internal manifest which specifies which services are started on the T2. This includes remote XPC service daemons, which we'll talk about later, file system checkers, upgrade and recovery agents, and many, many others. The one we are most interested in is Mac EFI util. Mac EFI util is the main T2 userland interface for managing UEFI firmware and non-volatile variables. It also has some additional functionality to dump and restore certain Intel ME related regions out of loaded firmware images, but we'll be focusing on the main initialization process here today. Mac EFI util starts off by examining the device tree to validate that the platform is actually slave attached flash capable. Then it grabs a signed image 4 binary off of the T2 file system, which contains the UEFI firmware, and loads it into a memory buffer. This memory buffer then gets marshaled to the T2 kernel, where the Mac EFI Manager kernel extension takes over the loading process. The EFI Manager implements all the functionality exposed from Mac EFI util. It manages NVRAM variables, the UEFI loading process, as well as it contains a number of state machines to keep track of various boot flows. So you wouldn't want to, for instance, change the UEFI firmware out from underneath a running system. The first thing that the EFI Manager does is it checks to see if the UEFI firmware has already been initialized. If so, it bails out quickly. Now, it's important to note that the actual loading of the UEFI firmware happens fairly rarely. Once it's loaded successfully, it is stored in a durable storage media and is only changed if the firmware update is available or the T2 itself resets. Once a decision has been made to actually load the firmware, the EFI Manager reaches out to the Apple Firmware Update kernel extension, which verifies the cryptographic signature of the firmware package against the Apple root CA key. If this check succeeds, then the UEFI payload is copied over to a storage region inside of the T2. Then something really peculiar happens. The EFI Manager checks to see whether the T2 has had its production mode fuses blown, and depending on the state of that and an overriding T2 boot argument, it writes one of two 64-bit indicators into the loaded UEFI firmware image. What these indicator values actually do is yet to be fully understood, but at the moment that the firmware is being provided to the actual system, it invalidates its own cryptographic signatures. So, once this is done, the EFI Manager configures a bit of internal hardware we call the eSPI slave-attached flash DMA engine through a series of memory map configuration and status registers. This configuration redirects eSPI slave-attached flash read and write operations to the internal storage area. Now, it's important to highlight that this includes write operations. The traditional SPI flash chip is used as a durable, mutable storage media. Many low-level subsystems, such as the Intel ME, utilize it for storing configuration and state, and as such, it must be a bidirectional interface. Y'all can probably guess where this is going, but more on that in a little bit. After the DMA engine is configured, control flow returns back to the userland Mac EFI util, which informs the SMC by way of a couple other kernel extensions that the firmware is actually ready to boot. Then it lets the T2 go into a low-power sleep state, which is akin to turning off the screen of your phone. At this point, the system is finally actually ready to start booting. You press the power button, that triggers a notification from the System State Manager kernel extension, which then notifies the EFI Manager so it can update its internal state. After that completes, it sends a do S0 message to the SMC, where S0 is the fully on ASAPI power state. This effectively turns on the x86 side of the house. This brings the x86 CPU out of a reset hold state and allows it to begin booting the verified UEFI firmware image out of the T2 by way of that slave-attached flash DMA engine, ostensibly closing the gap of an unverified pre-verifier. So we end up with a functional flow of this. How can someone leverage the properties that we have learned to actually take control of the secure boot process? Well, as we discussed earlier, the chipset not only reads data out of the storage area, but also writes to it as it's used as a mutable storage area by the ME and other systems. And the firmware validation initialization is only done on rare occasions, either when there's a system upgrade or the T2 crashes and reboots. How often the T2 actually reboots by itself is not known to us, but I speculate that it's actually a fairly rare occurrence in battery-backed systems like the MacBook. So from a hardware perspective, the T2 is attached to the chipset by a series of wire traces. This means that if an attacker can locate those traces and get on that eSPI bus, they'll be able to overwrite the UEFI firmware stored internal to the T2 in a manner similar to the chip clip approach that we saw earlier in the EvilMate attack. In theory, this would only give limited persistence until the next upgrade cycle, but the infected macOS kernel could prevent that upgrade process from ever running, or at least until the T2 reboots. Or, if we can actually compromise the T2 kernel, we could overwrite the internal storage from the inside without having to resort to physical attacks on the platform and have actual true persistence. But for that to happen, we need a way to actually target and interface with it. The T2 exposes many services to the macOS operating system that may provide a beachhead for exploitation. To explore this area further, I'm going to hand it off to Jeremy to talk about these services and actually how to communicate with them.
Thanks. Thanks, Mikhail. So the T2 chip runs a number of services on behalf of your Mac. These are things like biometrics, such as Touch ID, the Find My Device feature, which you may be more familiar with on your iPhone, speech recording for Siri, as well as system diagnostics functionality that we'll talk about a little bit later. And if it's possible to communicate with these services, it may be possible to exploit these services. And if we could combine an exploit that gives us remote code execution on the T2 with a BridgeOS kernel vulnerability, we may be able to overwrite that vulnerable flash purely through software, which would be really cool. So the majority of the rest of this talk is going to focus on what does this interface look like that the T2 chip exposes to the macOS host. Luckily for us, as researchers, macOS comes with this nifty utility called remotectl. Remotectl provides a variety of different functions for us to talk to the T2 chip. Starting off with the list command, we can list the T1 or T2 device that's attached to our macOS host. It shows up as local bridge. And if we use the show command, we can print out a variety of different properties about the T2 chip, including a list of the services that are running on that T2 chip that are available for us to communicate with. We can then turn to the netcat or the relay subcommands to actually communicate with these processes. Netcat will open, will allow us to use standard input and standard output. Relay will actually open a listening socket on the macOS host that we can then attach to with our own process and send traffic to the service that we've targeted. But before we get into talking with the T2 chip directly, let's step back and look at what the communication channel with the T2 actually looks like. The T2 uses Apple's proprietary IPC protocol, XPC, and the remote XPC library to communicate with the macOS host. This protocol has a programmer API, but the actual message format is proprietary, probably because Apple wants the ability to change it whenever that may be warranted without causing people to have things break under them. But it makes things a little bit trickier when we're going to be looking at some network traffic later and we don't know what that format looks like. The T2 exposes itself to the macOS host as a USB-attached network interface over the PCIe bus called EN6. And this interface is protected by SIP, System Integrity Protection, so we can neither read nor write it. It's also worth noting that the T2 chip and the macOS host over this interface have static fixed IPv6 addresses and static MAC addresses. We found this to be common on various systems that we tested. Now, at the time we originally did this research, it was not required to disable SIP or use root to use the remotectl relay command. However, as of 10.14.3, remotectl needs a little bit of help to work, and we'll go into that a little bit later in the talk. If we do disable SIP, a new interface becomes available for us to use. The VHC 128 interface behaves like a span port for the EN6 interface. That means that all of the network traffic that would normally traverse the EN6 interface becomes replicated on the VHC 128 interface. And if we turn to our favorite aquatic packet capture tool, such as TCP dump or Wireshark, we can then start capturing some of that traffic and taking a look at what it looks like directly. So you'll see here, there's some low-level USB-based traffic, there's TCP protocol, there's even HTTP2-based traffic. And if we dig into some of that HTTP2-based traffic and we look at some data packets, we can see some information here, mostly a lot of dots, because this is all binary encoded data. We do see a small substring request underscore type, but that doesn't really mean anything to us at this point. So we're going to continue, before we talk about interfacing with the T2 chip again, we're going to take a moment to figure out what it is the T2 chip is saying as a way to build some tooling that will allow us to interface with the T2 chip later. These are all the different layers that the T2 chip traverses, or packets. These are all the different layers that make up packets that the T2 chip uses to communicate with the macOS host. We're going to start over on the left with the MBIM layer. Now, MBIM layer, if you're not familiar with it, I wasn't before we were working on this project, is a USB-based network layer that encapsulates multiple Ethernet packets for transit over a USB-based network interface. It's interesting that in many cases for large data transfers, the information will be split up into multiple MTU-sized chunks at the TCP layer, only to be re-encapsulated into one giant packet at the MBIM layer. The Ethernet, IP, and TCP layers are nothing special, so we're not going to go into them. But at the HTTP2 layer, there is something worth noting. Now, for those of you who are not familiar with HTTP2, I'm going to give a very brief crash course on how it works. So in HTTP1, you have a client and a server, and the client, such as a web browser, will make a request to the server to retrieve some page content. And in the process of doing this, it will it'll perform a TCP handshake, probably these days a TLS handshake. And it will then make a request to retrieve the data, pull down that data, and then it will discover, upon retrieving the page data, there are a bunch more resources that I have to make new requests to go out to that web server. And so having to go through more TCP handshakes, more TLS handshakes, et cetera. This is very cumbersome, very slow. We want something more efficient. So HTTP2 is designed to build a single persistent connection upon which multiple page requests or other kinds of requests can be multiplexed to avoid having to do all these TCP and TLS handshakes. So in HTTP2, we have this new concept of a stream, and a stream is roughly analogous to one of the old HTTP1 connections. A stream can be opened by sending a headers frame, and in the headers frame, typically you would pass HTTP headers. Once a stream is opened, you can send data bidirectionally to either the client or the server through the use of data frames. Now, Apple uses this in a non-standard way. When they open new streams with HTTP2 headers frames, they don't actually put any HTTP headers in them. This actually breaks the HTTP2 spec and was a little bit of a surprise for us when we were reversing this, because it meant that the standard HTTP2 libraries don't work. So we had to make some changes, and then we could move on. So we'll talk a little bit more about that in a little bit. Above the HTTP2 layer is a new layer that we haven't seen referenced in any of the other XPC third-party documentation before. For lack of a better term, we're calling this the XPC wrapper because it tends to wrap XPC objects. The XPC wrapper has a 4-byte header or magic bytes field, a 4-byte flags field. Now, these were the flags that we observed. This is a 32-bit field, and so there are likely many, many more flags. Hopefully, you will discover some and share them with the community as well. Follow that, there's an 8-byte length field for the payload that comes after, followed by an 8-byte message ID field. The message ID field is often incremented between request and response. The use of it differs between the different application protocols. So we've also seen it being used for signaling to identify which request a particular response refers to. Moving on. The last thing in this layer is the actual XPC objects themselves. And this will end up being sort of the meat of the reversing of this protocol that we did. Now, there's relatively little third-party documentation on this XPC serialization format. So when we started off, we did what many people do, and we tried to serialize some objects ourselves. Now, Apple does publish a programming API for XPC, and so we were able to create a little toy example application, some of which we'll show here, where we can create an XPC connection object, then create an XPC dictionary, a dictionary being the base class that all XPC messages must be made from, and then we can send that message over the wire. And you can see here how we can insert additional data into that base dictionary object. that may be data that we want to send over the wire. So here we're inserting a bool and int a uint64. And if we pay special attention just for a moment to this inserted value with a dictionary key of uint64 and a value of deadbeef, when we step through in our debugger to see how this is actually serialized, we can then find that flag uint64, or that string uint64, and we can begin to uncover how these messages are actually serialized out. Don't worry about this slide in particular. There will be more examples in a minute. Now, every XPC object starts with an XPC header before the main base dictionary object. This XPC header is made up of four magic bytes followed by a 4-byte version number. It's interesting that the version number is, at least from what we noticed, is version number 5, which is the same as what's shown in Jonathan Levin's StarOS internals. But the magic bytes appear to be different from any other known use of XPC. Now, before we get into how these XPC objects are actually composed, every XPC object will start off with a 4 bytes type field. And initially, we were able to retrieve some of these and figure out a limited set of them just based on observing various objects. But there were lots of holes. For instance, an XPC array is E0000, an int is 03000. We didn't have all of the types in between them. So we turned to the remote XPC library and did a little bit of data mining. And we ended up getting this entire list. And the XPC types shown here in green were either the XPC types that we were able to serialize ourselves, or XPC types that we were able to observe in the communication between the T2 chip and Mac OS. And so we were able to decode how these XPC types were constructed. The types shown in red were either objects that we weren't able to observe, for which no programming API was available, or they were types that maybe are not serializable at all, such as an XPC connection object. Now, for these next 3 slides, we're going to cover 3 different general categories of how these XPC objects are constructed. The first of these categories is fixed size objects, such as booleans, integers, etc. So in this case, as a fixed size object, a uint64 has a known length of 8 bytes. And so this is relatively simple. We have our 4-byte type field followed by our 8-byte known length value field. Moving on to the next general category, these are our variable length types, such as strings. And it will look pretty similar, except for the inclusion of a new 4-byte length field. So for our example string, duolabs ! It's important to note that strings have to be null terminated. So the null character at the end of the string, bringing it up to 9 characters, is reflected in that 4-byte length field. Now, another property of XPC objects is that every field within an XPC object has to be 4-byte aligned. So in addition to it being 9 bytes in the length field, it's actually going to it's going to be padded by 3 bytes and take up 12 full bytes. The third category of XPC objects are compound objects, things like dictionaries and arrays. And again, this will be similar to the variable length objects, but with an additional field here. So we have our 4-byte type field, our 4-byte length field, the length field reflecting the number of bytes for everything after the length field, and then a new field, number of entries. And this is what allows us to parse through the compound object and determine what its recursive sub-objects are. After that comes a concatenated list of all of the other objects within this compound object. Now, dictionaries are a little bit of a special case because in addition to the values of those objects, we also need keys. And keys are very similar to the string object that we saw in the last slide, except they don't have their own type and length field. So they're null terminated strings padded out to be a multiple of 4 bytes. So you can see here we have our 3 type, length, and number of entries fields, followed by our first object's key, and then the value of that object, and then our second object's key, followed by the value of that object. Now there are other XPC object types that we aren't going to go into in this talk, mostly due to the fact that they tend to be unique, and so I'd be going over specifics for a particular object type. We do have more details about these in our white paper. So at this point, we understand how all the different network layers work. We understand how to decode and encode XPC objects. So let's go back and listen in on that T2 communication that we saw before. For this, we're going to use the sysdiagnose utility as a case study. The sysdiagnose utility, if you're not familiar with it, is a tool that goes and collects a bunch of metadata about your Mac and sticks it in a tar.gz file for later perusing. And if you pass this utility the -C flag, it will also send a message to the T2 chip, which will ask the T2 chip to gather up metadata and send it back to be included in the sysdiagnose.tar.gz file. So we can use this as an easy way to generate some traffic to look at over the VHC 128 interface. And so this is what we were looking at before. And just as a reminder, this is what we were seeing in Wireshark. That was about as far as Wireshark could take us. And with the tooling that we built, based on understanding how these XPC objects are formed and all the different layers, this is now what we can see with this simple sniffer utility. We can see all of the fields available in the XPC wrapper, as well as the fields that are actually contained within the XPC objects themselves. So now that we understand this, sysdiagnose looks pretty simple. There's a simple message, request type equals 1, sent from the client to the T2. The T2 sends back a message saying response type equals 1, and then a few seconds later sends back a big data transfer that is the sysdiagnose tar.gz. So now, what if we wanted to talk to the T2 chip ourselves, specifically the sysdiagnose server running on the T2 chip? Could we write our own macOS client that, at least initially, just replicates the functionality of the sysdiagnose chip, or the sysdiagnose utility? For that, we're going to turn back to our friend remotectl. So, it went too far. The remotectl relay utility, again, will open a connection to a service on the T2 chip, and then open a listening socket on the macOS host, which you can see here with netstat, that we can then connect to with our own application. We initially tried to do this using Scapy, and that didn't work so well because it turns out Scapy's slow. And as the T2 chip is on your own device, it expects round trip times to be on the order of 1 or 2 milliseconds. So we needed something more performant. So we turned to the Twisted library and used the HyperH2 library to handle the HTTP2 layer. And then we built our sysdiagnose client on top of that. And at the time we were originally performing this research, it's important to note that root access was not required, SIP could be enabled, any unprivileged process running on the device could communicate with the T2 chip or with the services running on the T2 chip directly. Unfortunately, if you try this now, even with SIP disabled, even with root access, you're more likely to run into an error message that looks like this: no such process. Now, as security researchers, this is really unfortunate because we'd like to be able to continue poking around at the T2 chip, and we'd like to enable you all to continue to build upon this research. So we're going to step aside from our normally scheduled talk for a moment. We're going to show you how you can get remotectl to work again, if you would like. The remotectl relay subcommand specifically is gated by a new entitlement in 10.14.3 and onward. It's the com.apple.private.network.intcoproc.restricted entitlement. And using Jonathan Levin's really cool JTool utility, you can take the remotectl binary and add this entitlement to it, and then re-sign it with your own certificate. Now, in doing this, the amphidaemon is going to be very upset if you try to run this new self-signed remotectl binary. And so you'll need to disable that as well. But once you do, you have a remotectl functionality that you can use again. So we have to disable SIP, run it as root, disable amphid, and self-sign the remotectl binary. But once you do that, it's easy. Back to the sysdiagnose client. So with our initial with the original sysdiagnose-c, you can see that the message that gets sent is request type equals 1, and the response ends up looking like response type equals 1, some metadata about the file transfer that's going to come back, and then the file name. If we notice that if you pass some additional parameters to the sysdiagnose utility, it puts more things on the wire. It sends more parameters to the T2 chip. And so we wondered what other parameters can be sent to the T2 chip. And for that, we went and we looked at the firmware images that were extracted, that we showed you how to extract earlier in the talk. And we went and we grabbed the binary for the T2's sysdiagnose server. And we were able to pull out all of the different parameters that this particular server would be responsive to. And if you look at just the archive name, probably the simplest example, if we then use our custom sysdiagnose client to pass this archive name parameter, we can see that we get a new archive name, just as a proof of concept here. Now this is as far as we've gone, and we're unlikely to revisit this work anytime soon. So there are a lot of really cool things that can still be done here. There are lots more services to be explored. Fuzzing some of these services would be a great next step. And as the T2 chip is arguably the most secure boot process, or lends itself to the most secure boot process currently out there, this work is very valuable to the community to validate this process. And in the effort to democratize security, we are open sourcing all of our tooling, both the sniffer utility and sysdiagnose client as reference examples for how to listen and speak to the T2 chip, as well as all the underlying libraries that allow you to decode the message layers, decode and encode XPC objects, and make it all possible. Our papers are here at the short links shown. If you have any questions, we'll take them now, and thank you all for coming to our talk. Oh, and if everybody could use the microphone. Oh, you're at the microphone. Sorry about that.
Yeah. Hi. Thank you for the great talk. Could you elaborate on if and how third-party operating systems could interact with the T2 chip? Is it just a matter of implementation, or is there like a technical restriction?
How the Mac OS system?
No, of third-party operating system, if and how they could interact with the T2 chip.
Yeah, so to get third-party operating systems like Windows to boot on T2-enabled platforms, Mac EFI Manager has some additional flows in there to defer various keys to be Microsoft's as opposed to Apple's internally. So there are specific whitelists internally for Windows. They don't exist for Linux.
Can they also interact with the T2 chip in the same way that macOS can, using these messages?
I mean, it's, I have not tried directly, but I can't imagine it to be very different as it's exposed through USB to the host operating system. But I'd imagine you might be able to get something akin to the EN6 interface under Windows.
Hi. Can you explain more about the exploitation mitigation there are in the T2, like that execution prevention, SLR, Canary? Is there anything like that over there?
Sorry, could you repeat that one more time?
What are the exploitation mitigation in the T2? SLR, that execution prevention, stack Canary, is there anything over there?
Yeah, absolutely. All those mitigations are in place. It's basically an Apple Watch on your motherboard. So all the typical things you would find on an iPhone or watchOS, you're gonna find on the T2 itself. So with the A10, you're not gonna have like PAC enabled, but you're gonna find everything else.
Hi there. This side. Hi there. What components have you found are necessary to communicate with the T2 directly? I mean, on the iPhone, you have the EEPROM that needs to be signed with the actual CPU. Is the T2 encapsulated all of the components physically?
The T2 is encapsulating all those components. The SPI flash chip is no longer present on the board. Outside of the iMac Pro, it has a separate SPI flash chip for graphics card firmware. But their UEFI is all being provided dynamically by the T2.
Okay. Does the Touch ID, for example, need to be physically that same exact Touch ID to be able to communicate with the T2 to boot up and be able to see the data?
So we didn't specifically look at Touch ID, but Touch ID should be handled by the T2's SEP that is internal to that.
Okay. All right. Thank you.
So the SPI flash replacement issue you guys highlighted, shouldn't Intel's ME also address that through its secure boot process? If so, what does the T2 bring on top of that for secure boot, since Intel's ME also has an on-chip boot ROM as well as crypto key store, right?
Yeah, so we didn't see any signs of BootGuard being utilized anywhere, and Apple seems to be invalidating their own firmware signatures immediately upon loading, so I'm not sure how much that would help outside of doing individual like UEFI partition checks.
I see. All right, thanks.
Alrighty, well, thank you so much.
Thank you.